students, welcome to my YouTube channel. This is the 35th lecture in lecture series of linear algebra. In this video lecture, I will be discussing the theorem, that is the fundamental theorem, which is dealing with inverses, or it is called as invertible matrix theorem. Since I have used the statement of invertible matrix theorem in my previous video lecture, so I have made this video lecture clearing the concept of invertible matrix theorem. But before we study the concept of invertible matrix theorem, let us be familiar with few terms which I will be using in order to describe this theorem. So let me recall few definitions. So the first definition for the day is, what do you mean by invertible? So when I talk about invertible, I mean a square matrix A is invertible. The other name which I use for invertible is non-singular. So you should be familiar with all these terms. So a square matrix A is invertible or non-singular if there exists a matrix B such that if you multiply A with B, you get an identity matrix, and even if you multiply B with A, you get an identity matrix. We say that B is inverse of A. So this is the definition of invertible or non-singular. So a very important remark here which you should be very much clear, that not all square matrices, because in the definition I have used the word square matrices. So I want to make one point very clear, that not all square matrices are invertible. So we can see a counter example. Even you can make a very simple example. So this is a 2 cross 2, this is a square matrix, this is not invertible. Why? Because the determinant of this matrix is 0. Fine. So then we have a theorem dealing with this. So you should be very much clear with this theorem. The theorem states that if A is an invertible, then its inverse is unique. So the inverse is always unique. And a remark I must add here again, which states that when A is invertible, we denote its inverse by A inverse. So that is how we denote the inverse of A, if provided if A is invertible. Clear? Now moving on to one of the important theorem which I will be using in order to prove the fundamental theorem, and the statement of the theorem states, so the theorem states, if A is an n cross n invertible matrix, then the system of linear equations given by Ax equals B has the unique solution that is x equals to A inverse B. Fine. So let us prove this theorem. So what this theorem states, that if A is a n cross n invertible matrix, then the system of linear equations given by Ax equals to B has the unique solution, and the solution is nothing but x equals to A inverse B. So we need to prove this theorem in two parts, that is the existence first part, and then it is talking about the uniqueness part. So let us prove this theorem. It's very simple theorem, so I'll be assuming since it is given to me that if A is an n cross n invertible matrix. So my first assumption will be that let A is a invertible matrix. So let A be a invertible matrix. Then we have, so you can just manipulate this, A into A inverse B. Now since we know that associative law holds, so by the associative associativity of matrix multiplication, what I can write, so I can write A into A inverse B as A inverse into B. This is because of the associative property. Again, we know the definition of inverse. So A into A inverse is identity. So by the definition of inverse, we can just compute the value of A into A inverse, that is nothing but identity. And identity into B. Now by the definition of identity into B will be nothing but B. So what you get here is A into something is equals to B. So what I will be doing is I will be saying thus my x was nothing but A inverse B, and this x equals to A inverse B is a solution to Ax equals B. Now this I have proved as the existence part. Now what about the uniqueness part? So in order to prove the uniqueness part, so I'll be assuming one more solution. So uniqueness, let y be another solution. So if y is another solution to the linear system of equations, then it follows that ay must be equal to b. So ay must be equals to b by the definition, but multiply both sides with A inverse. Now multiply both sides with A inverse. So if you multiply both sides with A inverse, what you'll get? So this will be A inverse A into y is equals to A inverse B, and A into A inverse is nothing but identity. So this is identity into y is again y, correct? So y comes out to be equals to A inverse B, and what I have assumed as my A inverse B, that was nothing but x. So y comes out to be equal to x. So this proves that my identity is always unique. Now, after proving this theorem, let us move to the main objective of this video lecture, that was the fundamental theorem. The fundamental theorem of invertible matrices. Invertible matrices. Correct? So the statement says, if we consider any n cross n matrix, that is for any n cross n matrix, the following are equivalent. The following are equivalent. So what are those following statements? The first statement is A is invertible. The second statement is Ax equals B has a unique solution. For B coming from R, for B coming from Rn. The third statement says Ax equals 0 has only the trivial solution. And when I say trivial solution, what I mean that at x must be equals to 0. That is the only solution for the above system. And the fourth statement is the row reduced echelon form. So I'll be writing the row reduced echelon form as row reduced echelon form, RREF, of A is nothing but identity. So I'll denote identity with capital I. And the fifth equivalent statement is that A is a product of elementary matrices. So that is what my statement of fundamental theorem of invertible matrices states. Now what is my strategy if I want to, so what will be my strategy when I say I want to prove the fundamental theorem of invertible matrices? So I'll be starting from A, or I'll be starting from the first statement, I'll be moving towards the second statement. From second I will be proving third, using third I will be proving fourth, using fourth I will be reaching out to fifth, and using fifth I will be reaching towards first. So that is what my strategy will be in order to do the proof. So that will be the strategy, proof strategy, correct? Now let us see the proof. So the first statement says if A is invertible, then Ax equals to B has a unique solution for B coming from Rn. So you can easily compare the theorem which we have studied today in the first. So this is nothing but the theorem which we have already studied, that if A is an n cross n invertible matrix, then the system given has a unique solution. So can I say that first implies 2 is already done? So proof equation 1 implies 2. So this is already proved above, already proved. Now let us move from equation second to equation third. That is how we prove in mathematics the equivalent statements. So the second statement was Ax equals B has a unique solution, correct? And the third statement says that it has only the trivial solution. So using second statement, so let us see how we prove this part. So if Ax equals B has a unique solution, if Ax equals B has a unique solution for any B, so just look at the statement again, for any B, fine, for any B. So in particular it will also hold for 0. In particular it will also hold for 0, so that is Ax equals 0 has a unique solution. If my equation Ax equals 0 has a unique solution, so we know that the only solution for this system is nothing but x equals 0. Since x equals 0 is a solution to Ax equals 0, so it must be unique one. It must be unique one. So I have used the second statement and I have proved the third statement. So I am done with this arrow. I am done with this arrow. Now I'll be using the third statement and I'll be proving the fourth part. So what my third statement says, that if Ax equals 0 has the only unique solution, that is x equals to 0, then the row reduced echelon form of A is nothing but my identity matrix. So that is what I need to prove now. So if Ax equals 0 has just the trivial solution, so what was my trivial solution, that is x equals 0, correct? Then that is x equals 0, then the system of equations so in the reduced form is so what should be it? It should be that x1 must also be 0, correct? x2 must also be 0, and so on, xn must also be 0. So can I write it as 0 times or 1 time x1 plus 0 time x2 plus 0 time x3 plus 0 time x4 and so on to 0 time xn equals to 0, right? And the second statement 0 time x1 plus 1 time x2 plus 0 time x3 and so on to 0 time xn equals to 0. And my final statement will be 0 time x1 plus 0 time x2 plus so on to 1 time xn equals to 0. So if I convert the above system of equations in matrix form, I'll be writing here as 1, 0, 0 and so on to 0. For the second row, I'll be writing 0, 1, 0, all other entries to be 0. Similarly, 0, 0, 1, all other entries to be 0. And if you go on completing this matrix, in the last iteration, you'll be getting 0, 0, 0 and the last entry will be 1. Correct? And then you can multiply this with x1, x2, so on to xn. So the row reduced echelon form of A has come out to be an identity matrix. So that is what I wish to prove from third till fourth. So I have proved using third the fourth part. Now I'll be using the fourth part, that is the row reduced echelon form of A is identity, and what I wish to prove is that A is a product of elementary matrices. So I'll be proving 4 implies 5. That is, if the row reduced echelon form of A is nothing but identity, then I wish to prove that A is a product of elementary matrices. So let us see how to prove this. So if the row reduced echelon form of A is identity, then there is a sequence, so let me call it as say K, correct, EROs. So what does it mean? This means elementary row operations. So if the row reduced echelon form of A is identity, then there must be a sequence say K of EROs, that is elementary row operations, that will reduce A to identity. Correct with this? So each such ERO is equivalent to multiply A on the left by elementary matrix. Thus, so if the row reduced echelon form of A is identity, so there must be some sequence of EROs, that is the elementary row operations. So that will reduce my A to identity matrix, correct? And each such elementary row operation is equivalent to multiply the matrix A on the left hand side by elementary matrix. So that does it means, so thus there are K elementary matrices, and let me call those K elementary matrices like E1, E2 and so on to Ek, such that they will satisfy this property. What does that property states? That if you multiply A with E1 and E2 and so on to En, you will be getting nothing but identity matrix. Now, since my all EIs, that is E1, E2 and so on to Ek, I can call them as elementary matrices even. So these are my elementary matrices. And since all my elementary matrices are invertible, so can I write it as, so this implies that my A can be written as E1 inverse, E2 inverse and up to so on to Ek inverse. So I have proved my fifth part, that my A is nothing but the product of elementary matrices. So these are all my elementary matrices. So the last thing which I need to prove before completing this proof, that is 5 must also imply 1. You can easily verify this part from the above equation. Since each of my E1 inverse, E2 inverse and Ek inverse, all of these are invertible and this is equal to A, so A has to be invertible. So that is what I wish to prove from fifth implies 1. So since E, so I can write that since A is a product of invertible matrices, so A itself is invertible. So that completes my proof. So I hope you have understood this proof of fundamental theorem of invertible matrices. If you have any doubt, you can mention your doubts in the comment section. Stay tuned, and for more such video lectures, do subscribe to my YouTube channel and do not forget to press bell icon. Thank you.